Greetings and thank you for joining us for today's webinar on vision-based cobotics research with our latest robotic offering, the QArm. My name is Armin Molki and I will be your host and moderator today. Today's presenter is Mr. Murtaza Bohra. He is a research and development engineer as well as the academic lead for the QArm manipulators curriculum. Murtaza previously designed the application architecture for Quanzer's unmanned vehicles, the QCar and QDrone. With a master's degree in robotics and a background in aerospace engineering, both from the University of Toronto, he continues to be involved in academia as a sessional lecturer teaching a graduate course on serial manipulators and mobile robotics at the University of Toronto. And with that, Murtaza, the floor is all yours.
Thank you, Armin. Okay, welcome everyone. I'm glad you could be here today. I want to talk to you about vision-based cobotics research with the QArm serial manipulator. According to the founders of the term Cobot, it is an apparatus and method for direct physical interaction between a person and a general manipulator controlled by a computer. According to the International Federation of Robotics, collaborative manufacturing applications can be classified into 4 different levels. In the highest level, a human and robot work alongside each other, but with no shared workspace, something referred to as coexistence. Given constraints in space, the second level combines the physical workspace of the manipulator and the human, allowing the two to share such a workspace. However, the two cannot actually operate at the same time. This essentially separates their workspace temporally instead of spatially, referred to by the IFR as sequential collaboration. In the third level, humans and manipulators can operate at the same time and even work on the same part or machine. However, they come in no contact with each other. This contact, of course, could be deliberate and physical, but from an abstract perspective, this also refers to any tracking or sensing from the robot's side. The human operator could, of course, be keeping an eye on the manipulator and its motion, but not vice versa. This level, called cooperation, is the first to allow the robot and human to share their workspace, both spatially and temporally. At this point, we can start seeing that we're running into concerns about human or operator safety. In the fourth and final level, the robot corresponds in real time to the worker's motion. The robot must maintain an active awareness of the location and motion of the human operator and always take precautions to not harm the worker in any way. Now we are talking about added sensor suites on the manipulator, vision, and potentially artificial intelligence as well. The QArm serial manipulator is a 4-degree of freedom manipulator that can be used for cobotics research. There are numerous aspects of collaborative robot design and research that could be validated in a controlled and safe manner using this platform. If you have an idea in your mind, you can manifest it on the open architecture canvas of Simulink, deploy it in real time using our software Quark, and tune it while it's actually running. The demo that I'm going to show you today began in my lecture room a couple of weeks ago. In addition to being a research and development engineer at Quanzer, I'm currently also a sessional lecturer at the University of Toronto, where I'm teaching a graduate course in manipulator robotics. We were at a stage in the course where we discussed robot vision, and after an overview of common topics such as color spaces, thresholding, blob detection, etc., we looked at a visual servoing example using the virtual QArm manipulator. All the students had access to this virtual manipulator on their own laptops via the Quanzer Interactive Lab solution, which allowed them to try this example themselves. In this example, the object is stationary and my arm is responding and moving so as to bring the object in the image at the desired pixel location that you can see me setting at the bottom left of the screen. After this lecture, I decided to try this on the hardware at home. Now, the object itself in this example can also move as the arm is tracking it. The arm moves horizontally and vertically by directly actuating the manipulator in joint space. A horizontal pixelator is removed by actuating the base joint of the manipulator about the vertical Z-axis. And a vertical error is negated by actuating the elbow joint, making the problem a rather simple one and based purely on joint space calculations and kinematics. The tracking itself can vary dramatically with different lighting conditions and the size of the object in the image. So if I were to take a few steps backward, the lid of that vitamin bottle would be very small, and my algorithm most likely will fail to pick it up correctly. To increase my personal sense of security, I did two things in this demo. Firstly, if the object disappeared, the arm would return to a known starting location, in this case, the position where it's facing me. And you will see this in a minute when I take that bottle and yank it out of the workspace and the arm faces me directly. Secondly, I placed additional safety limits to shut the controllers if the speed ever exceeded 45 degrees per second. That's really slow, but this gave me a lot of peace. It felt great at the time I recorded this demo, but come on, safety by means of limitation doesn't actually help me sleep at night. I did not intend to handicap the manipulator or its capabilities. Rather, I wanted the arm to have more freedom and start tracking how far away it was from me. I reminded myself that with 2 degrees in engineering and over 7 years of experience working with robotics and automation, manipulators should be afraid of me and not the other way around. I decided to repeat this demonstration, but now with the added capability of tracking the distance between myself and the robot using stereo depth camera on board the manipulator. And so with that, I'm not going to waste any more time. Let's get into the actual demonstration. This is going to be in Simulink. So on the left right here, you can see a Simulink model visual servoing. And then on the top right, this model spawns a video display that is showing you the depth and RGB information from the camera that's on board the QArm. And then in the bottom left, you see I have a webcam right here that has that's showing you the QArm manipulator with the camera on board as well. And so before I run the demo, let's go through it to get a sense of what exactly is going on. So everything that I have in red, which are these subsystems, are doing some form of input-output. They are capturing information or writing information to a device. So here I am capturing very simple toggles or trigger values from a Logitech joystick that I have. I'm not interested in using the joystick to drive the manipulator. Instead, what I'm doing is grabbing Boolean values such as track, grab, or color that allow me to change certain aspects of the code. Then I have an image acquisition subsystem that is capturing depth as well as RGB data. And then this subsystem is the hardware plant that allows me to read joint values from the arm, as well as write the intended joint commands and whether or not I would like to actuate the gripper. So I am actuating the arm in position mode, and the low-level controllers are handling the motion for me. In addition to that, then I have two green subsystems. These are for image processing. And then I have some logic and timing, and then some kinematics in orange. So let's start by looking at the image processing subsystem here. I have both RGB processing as well as depth. And the idea is to take your RGB image, convert it from RGB space to HSV, threshold for a green or a red object, as you will see in a minute, and then take that bitonal or binary image and pass it to a blob detection algorithm that looks at connected components to label them. And that gives me the position of the blob it's found, and I pass that information to the depth processing. The depth processing then takes the entire depth image, and then after a temporal low-pass filter and a depth hole filter, it will then select all the depth pixels around the object's coordinates, average them to give me the depth to the object in meters. And so that gives me the X and Y location of the blob in the image, as well as the depth, which is the Z direction in the image coordinates. And I take that blob information and pass it out of the subsystem. I then pass that to visual servoing, which is also getting kinematic information such as the orientation of the end effector, as well as the Jacobian through differential kinematics. And I'm also passing it my desired coordinates for the blob. So you can see here, I want the blob to be in the center of my 480 by 640 image, and I want it to be 1 meter away from me. And if I pass it to this algorithm, after filtering the blob data, it is simply applying some scaling and sign correction. And that gives me end effector velocities in X, Y, and Z. I need to convert that into base frame coordinates. So I do that by using the orientation right here. And I take these base frame end effector velocities and turn them into joint velocities using the Jacobian. That then gets passed to the tracking logic, which says simple things such as, well, if you are being asked to track the object and you've actually found an object and you're not currently gripping the object itself, then proceed to integrate those joint velocities into joint commands and apply them to the manipulator. So now that we have an idea of what this is doing, I'm going to move this to the left, and let's start by actually running the demonstration. So I've used the monitor and tune button here in the hardware tab in Simulink, and that will build C code from this application and deploy it to my Windows machine as a controller, controlling the ARM via a USB connection. Okay, so now that the LED on the base has turned blue, the code is actually running. And here you can see that is me right here in red. At the top left, you can see two images. The first part, which is on the left, is the depth data. So as my arm moves closer to it or further away from it, you can see my depth changes. And I'm applying a color map so you can visualize the depth a little easier. Now, it is coincidence that at roughly the desired distance, which is about 1 meter right now, the depth data is actually red and I'm wearing red, but that again is a coincidence. This wasn't planned. But what I'm going to be doing here is I have an object right here that I've picked up. This is green, of course, and I want the camera to track this object. So based on the videos that I have posted on LinkedIn in the past, and you saw me show you in the presentation, what the arm would do is track it left and right. But in this case, it will also track depth to the object. Now, before I run it, I have to tell you how exactly I'm using this joystick. And so on this joystick at the very top, I have two triggers. And these are going to allow me to ask the arm to start tracking me or stop. And it's going to allow me to pick the color of the tracking. So you can see here that the webinar screen sharing is starting to slow down my controller a little bit here. And I think it's back. There we go. Okay. So let's go back to this object. The yellow line is drawn from the center of the RGB image to the current location of the blob, and it should give you a sense of where the arm will respond and move towards. So if I use the first toggle, it will go from tracking me, this object, which is green, to tracking me, which is red. But I want it to track the object right now. Let me hit the second toggle. And right here, you can see the arm starting to track this object. As I move further away, it comes towards me. If I go closer, it moves back. But I can move it around, and it tracks the object. Now, at the same time, I could tell it to simply start tracking me. And so this is where I am. And let's see if it actually tracks me as well. And it's trying to keep 1 meter of a distance from me as I move around in this space. And that right there was a workspace singularity. So you can see that the LED has turned red, the model has actually stopped, and this was the speed safety limit that I had put into place. So I got a message right here. The arm was moving close to a maximum speed. And so that has stopped this controller, which was designed by safety. So I can reset the arm by simply powering it off and restarting it and deploying the model again. There we go. Back to this object and being able to track it. So this is the idea with Simulink. You can easily change the controllers as you desire, monitor what's exactly going on in real time. If something happens, you can check out all your scopes to see what exactly went wrong and then retry again. At the same time, I can tell this manipulator to simply go ahead and grab the object. And that's the demo. So where do you actually go from here onwards, right? The depth data here is calculated using the left and right infrared cameras on the Intel RealSense right now. And I am using the depth data that's coming straight from the camera, but you could, of course, use the infrared directly to estimate your own depth and improve the depth quality. I'm also currently assuming that the depth and RGB feed share pixel coordinates because I have the same camera resolution. But the lenses have a small linear displacement between them, which needs to also be accounted for. You can also use the camera that's right here with pre-trained neural networks or object classifiers to recognize humans, recognize objects, and then take action based on that. You can add additional safety routines to avoid singularities. You could add your own sensors using the onboard end effector board that we have to sense them and actuate and get the data you need. You can also use the onboard current sensors at each of the joints to detect if the arm has come into contact with an object or a person. And you can add multiple cameras to track the workspace that is being shared between the human and the arm and identify both their motion. Now, the idea here is that it took me less than a week to develop and validate this demonstration on the QArm with my limited knowledge in robot vision. With your resources, knowledge, time, and an army of PhD students, I can only wonder where you can take your own ideas. If you have any questions, I will be happy to take them, and then I can also get into more details of the algorithm with you based on the questions.
Thanks, Murtaza. That was a fantastic presentation. I really enjoyed it, and I hope everybody else did as well. There's a couple of questions have come in. First one, is the solution out of the box a Cobot?
Okay, so the International Federation of Robotics defines, again, many different levels of collaboration between robots and humans. And so a manipulator being a cobot has to have a lot of onboard safety introduced by default. And so this manipulator is a 4-degree of freedom arm that can enable you to do cobotics research and implement your cobotics algorithms to verify that they work before you deploy them to other cobots. Now, more often than not, industrial cobots come with their own proprietary software, and this is a language that you as an academic may not speak. You might be comfortable with Simulink, with MATLAB maybe, with C++ even, or Python or ROS, but the proprietary software that the ARMs come with does not allow you to comfortably change the aspects of the design and experiment with it. So what this allows you to do is validate your algorithms comfortably and then figure out ways to actually deploy it on industrial cobots.
Thank you. Next question, how is the continuous controller being discretized?
So that is using our software Quark. So right here as the model is running, if I go back to the simulation tab, modeling tab, open the model settings, you can see that I have asked this entire model right now to run at 240 Hertz. And so this is turned into C code deployed on my PC, and then our software Quark is what makes sure that you are getting that sample time and that performance. So right here I have a timing subsystem that is showing you the sample and computation times on both the fast rate, which is 240 Hertz, as well as the image rate. So if I take a look at that scope, You can see the sample and computation times right here. So 240 hertz would be somewhere between 40 and 50 milliseconds. So you can see that is the sample time. And then you can see the computation time below as well. Now I can just assume that a lot of this is choppy because the screen is also being shared at the same time.
Great. Next question. What is the realistic upper limit of the sample time that can be used for a model such as this one?
So the QArm, all our default examples that come out of the box with it are all running at 500 hertz, but I believe you could push to 1 kilohertz with this manipulator. And that is for the base rate itself, but then you have additional processing for, let's say, the camera. The Intel camera that we have provided on here can do depth processing at up to 90 hertz and RGB processing up to 60 hertz as well.
Is there a teaching mode for path planning?
So the teaching content is very cascaded and limited to allow students to learn different concepts in a safe way. And so one of the labs there does actually look at path planning and trajectory generation. So let me share my slides again, and I can show you some of those concepts. So this is the core software that we used for the teaching topics. And then around that, we have built numerous labs. So you can see right here, one of the labs on trajectory generation does path planning using cubic splines as well as parabolic blends. But then after that, we get into differential kinematics and we look at tool manipulation, which does path planning using differential kinematics as well. And in the end, we also have an imaging example that ties back to the path planning routine for visual surveying.
Next question is, does it have a standalone mode or a PC should always be in the loop?
So a PC will be in the loop here. The ARM is directly connected to the PC or some compute board via a USB connection. So in this case, I am using a Windows laptop and my controllers are running here. You could instead also have a Raspberry Pi connected via USB, and you could be deploying your code to the Pi. You could also use an SPI connection. There is an SPI panel that you can replace the current USB panel on the ARM with. And now you could have SPI, any compute board that can communicate with it via SPI and your own software. You could use that as well.
Great. Next question. What are the range of speeds available for the ARM when tracking the object?
Yeah, so this comes down to the application at hand. So let me get into a little more detail here to first show you the safety limits that I placed here. So if I go into the hardware subsystem and my output, you can see that I'm monitoring the speed right now to say if it's greater than 90 or pi by 2, stop the model, right? Now you can see my comments here for 45 and 60, but again, the more comfortable you are with the ARM, you could change this. The actual ARM can move very fast. So with no payload attached, it can go up to 180 degrees per second on the different joints. But we place these safety limits. Now, these are what I call very soft limits because these are in your Simulink code directly. In addition to that, in the hill initialize routine here, you can also place certain hard limits on the speed as well as acceleration. So if I stop this model, probably from the hardware tab, or from the console. Okay, there. You can see that you can also place additional safety speed and acceleration limits right here. So for example, a lot of the student models for their curriculum come with 90 degrees per second and 60 degrees per second squared limits. So the arm moves very slowly and comfortably as they learn different topics. But if you set them to 0, that essentially sets no speed or acceleration limits.
Great, thank you. Can you comment a little bit further on the gripper itself? Are there different types of grippers that we provide, or is it just a single type?
Okay, so let me see if I can switch cameras here. There we go. That is the arm camera. So let's switch it one more time. Not this one either. There we go. So this is the camera that's on the object itself. And so now I can show you the gripper on the arm right here. So this is a 5 contact point gripper. You've got 1, 2, 3, 4, and 5 pads. This has actually got articulated fingers on each of them. And so when you tell it to grip an object, it grips by sensing current, and it will only apply enough strength to pull a certain amount of current from the actuator. And if it detects the object, let's say shuffling or fighting, it will loosen its grip as well. That again depends on the code I'm running right now. But in addition to that, you've got this end effector board right here on top that allows the user to add their own sensors to it. So this is the gripper that we provide with the arm right now. However, there is a standard ISO mount right here. So you could replace this with your own gripper design if that is an avenue you would like to pursue.
Thank you. I have another question. Someone is wondering if the arm can be installed on a moving base without losing precision.
Very interesting question. Please, for sure, try it. We would like to work with you to do that. The arm right here, if you notice, has mounting holes. It's hard to probably tell from there, but you could mount this platform directly to a mobile robot, of course, as long as it can provide the power that the arm needs. But the arm itself is pretty rigid. So right now it's attached rigidly to this base, and it has a repeatability metric of 0.1 millimeter. So I doubt it would change quite a bit depending on the performance of the mobile robot itself.
Speaking of mobile robots, there's a question whether it can be mounted on a Cobot. I know the answer is no, but I'll let you elaborate further.
Um, it depends on the, again, power requirements and payload and so forth. So when it comes to payload, I know for a fact that the QArm weighs just a little more than what the Cobot can take directly itself. In terms of power, that's another consideration to keep in mind. The ARM, of course, has a 12 volt, 16 ampere connector that is connected to it. And so when you're trying to move this around, it has a lot of juice. And I don't think the Cobot can actually provide it. But there are options that we are considering on the side. And if you are interested in something like this, a direct conversation could be initiated with that.
Another question I have, could you please describe in more detail how does the manipulator track the object that you used in this demo?
Sure. So consider here, this is the object again that I was earlier tracking. I'm going to turn off this arm so that I can freely move it around and talk to you about it. So as the object here moves sideways, I am asking this end effector to also linearly move sideways. So if you attach a frame to it, the z-axis going directly along the link, the x-axis going straight up, and the y-axis going towards the left right here. And so based on the horizontal and vertical pixel error, I command end effector velocities in the x direction, which is vertical, and y direction, which is sideways. And then based on the depth camera's information, which is the distance between the object and the manipulator itself, I command the end effector to move along its z direction. Once I have these velocities for the end effector, I use the orientation matrix 0R4 from the base to the fourth frame to transform those velocities back into base frame coordinates. And then I pre-multiply that with the Jacobian to convert them into tasks, joint space velocities, and then command that to the base, shoulder, and elbow joints. And that's how the manipulator tracks.
I have one final question, but before I ask that, I just want to correct something. The repeatability that we actually have is plus minus 0.05 millimeters for the arm.
Okay.
Final question, what is the maximum cable length with the arm?
The cable length, okay, so that depends on which cable, of course. The USB cable itself does not have a limitation. We provide one with it. The camera cable has a limitation for sure, depending on the resolution you're interested in getting image data at. So if you want the full 1080p RGB image, then you need to use the cable that we provide with the manipulator. Let me switch back to a camera so I can show you these cables. Okay. So notice right here that I've got a camera port right here. This USB cable is directly connected to my laptop, and its length is limited since I need the resolution from the camera to be maximum. If I use an alternate cable, you're going to get a lower resolution with a longer length. Of course, you could disconnect the cable from the base right here and directly connect it to the camera itself. So if I were to pull this cable out, and you can plug yours in directly into the camera, but this would be hanging over the manipulator. So if you were to focus on direct vision research with this arm and you were not interested in moving the manipulator around too much, this is also an option.
Perfect. Thank you again, Mortaza. This was a amazing presentation and demo, and a big thank you to all of you for attending our presentation today. Have a wonderful day, happy holidays, and stay safe, everyone.